probability of A union B equal to, then we have to prove that probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. This is we have to prove. So in this, the nature of A and B are not mutually exclusive events to each other. Then we have to prove that probability of A and B equal to probability of A plus probability of B minus probability of A intersection B. I will prove this theorem with the Venn diagrams here. Here, is it visible? Addition theorem. Addition theorem on probability. On two events. So let me finish first this, then we'll extend this theorem to up to exclusive events. Then prove that. What about the result? Probability of A union B equal to probability of A plus probability of B minus probability of A intersection B. This is we have to prove. This is called addition theorem on probability on two events. Okay, on two events. Probability of A equal to probability of A plus probability is result. I will go to use one diagram here. So what is A and B here? A and B are any two joint events. Means there is a common region exists in between A and B. Then we have to show that this. So for this theorem, I'll go to take one diagram like this. Suppose this is A, this is B, this is A minus B. Only this region, this part is A minus B, this region. Or we can write this as a intersection B bar or A intersection B complement. And what about this part? Only this part. This region is comes under the B minus A, or we can call it as a bar intersection B. Means it is here only this region. This is A bar intersection B, or only this region A intersection B bar. Okay, and this combined region is A intersection B. A intersection B. Okay, this is A intersection B. Now with this Venn diagram, I will prove these results here. So first, shall I write from this Venn diagram? A union B equal to yes, it is A union A bar intersection B. Yes, this is the major steps here from Venn diagram. A and B means complete this region, this part, this region. Okay, I'll go to write this is A union B equal to A union A intersection B bar. So here A means what about A? Yes, this complete circle A. Complete circle A is A, this A. And what is A minus B means, or A intersection B bar means only this portion, like this. Okay, but I'm not taking this one. I'm taking complete A, this circle A. And so actually A union B means we'll get this part, complete this part. A union B means from here to here. So I'm writing this A and this from the Venn diagram. A union A bar intersection B. So this is A, and A bar intersection B means B minus A, this part. So this region. Okay. Yes, it includes complete A and B here. It internally it includes intersection part also. So this is only A bar intersection B. This is complete A, and this is A bar intersection B. So it includes complete A union B quantity. So from the Venn diagram, I'm going to write A union B equal to A union A bar intersection B. For this, take probability on both sides. Take probability on both sides. So this is probability of A union B equal to probability of A union A bar intersection B. And here, what is the nature of A and A bar intersection B? So A is this circle, A bar intersection B means this part. So of course they are touching, but there is no common region in between these two. Means these two are disjoint events or mutually exclusive events. Is it clear? A is this circle, and A bar intersection B means we have the portion like this. Means they are touching, but there is no common region in between these two. It means these two are disjoint events or mutually exclusive events according to axioms of probability. If any two events are disjoint, then their union will become sum of their individuals. So it will become P of A. This union will become plus P of A bar intersection B. Since what about condition? Here A and A bar intersection B are mutually exclusive events, or simply we can call disjoint events. Because of that, I written their union equal to sum of their individuals. So next. So this is here. I'll write here. So what about this? So P of, so I'll write here, sir. So P of A union B equal to, I got P of A, same this step I'm writing here once again, P of A bar intersection B. Okay, next here. Now, I want to write this as a P of A and B equal to, I want to prove this result. For that, I am adding and subtracting right hand side A intersection B part. So P of A, same for this equation, A bar intersection B, plus I am adding P of A intersection B. If you cancel this, again we'll get the same this one. So next, P of A, and merge these two. Add this two. Plus P of A intersection B. These two are one set. And remaining minus P of A intersection B. Again, coming to the Venn diagram, what is A bar intersection B here? A bar intersection B means here from the Venn diagram, this part. A bar intersection B means this portion. We have like this A bar intersection B. This is A bar intersection B. And what is A intersection B? A intersection B means this part. This is A intersection B. So it includes this common region and only B. It indicates complete B circle. Is it clear? This is yes, A bar intersection B. And this region is A intersection B. Means it indicates completely circle B. So this is P of A plus complete B. This is probability of B minus probability of A union B equal to, finally we got this result. So here, what is condition? Here P of B is P of A bar intersection B plus P of A intersection B. Okay. So that's why I written this sum of these two is completely B circle. So P of A union B equal to P of A plus P of B minus P of A intersection B. So this is addition theorem on probability based on two events only. Same this theorem if you extend up to 3 events, 4 events, or up addition theorem on three events. Okay, come to the statement. Yes, in previously I have taken A and B are any two joint events, but here three events means let us take A, B, C. So if A, B, and C are any three joint events means definitely there will be intersection part must be exist. Joint events, or simply you can call it not mutually exclusive events. Then what you have to prove? Then prove that probability of A union B union out of NB, because that is on two events, but here it is on three events. Therefore, probability of A union B union C must be equal to probability of A plus probability of B plus probability of C minus their two intersections. Probability of A intersection B minus probability of B intersection C minus probability of C intersection A, then sum of triple intersection. Probability of A intersection B intersection C. This is the result. This is your two. Okay. So probability of A and B equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of C intersection A plus probability of intersection B intersection C. This is the addition theorem on probability on three events. With the help of these two events, proof only events. Okay. So first, come to A. This is B. The Venn diagram. I am going to prove addition theorem on C, and this is only A. See this part. This part is indicates only A. That is A intersection B bar intersection C bar, and this is only B. That is A bar intersection B intersection C bar, and this is only C. This is A bar intersection B bar intersection C, and these are the combination of two quantities A intersection C. This is A intersection B. This is, and this is B intersection C, and this part is combined three intersections A intersection B intersection C part. Okay, this is, but I'm not going to take this entire figure and a combination of this. Just I'll write this theorem with the help of addition theorem on two events. So first, probability of what is A and B? What is probability of A and B? A and B and C. First item, this is probability of A union B union C equal to first item. This is sum of two. That is probability of A union B. Take this is one combination union C. Okay, I am writing probability of A and B and C equal to probability of A and B is the one event. Assume this A and B is completely one single event, and second event is C. Again, it is in the form of A and B formula. Probability of A and B. So I converted three events problem into two events problem. That is A and B and C. It is probability of A and B union C. So assume A and B is complete one set. A, assume that is A, and C is B. So it is comes under the B equals C. So what is the formula? What is A and B formula? Just now we did that. That is probability of A and B section B. So apply same this formula. So assume this is A, this is some B. So probability of A and B equal to probability of A. Probability of A means probability of A and B plus probability of B. Probability of B means probability of C minus probability of A intersection B. So A means A union B. Probability of A union B in B minus P of A intersection B. Okay, this is. Now expand this to again one more time. Again A union B formula. So for this I can apply the addition theorem on probability on two ways. So it will become P of A. What is A union B formula? P of A plus P of B minus P of A intersection B. Okay, this is plus P of C minus. Now it is here. It is distributive properties. A union B intersection C equal to what is A union B intersection C formula? Yes, I'll write here. So A equal to yes, A intersection is a right distributive law. Okay, right distributive law. A union B intersection C equal to A intersection C union B intersection C. So expand this. So minus of is there. Minus of probability of A intersection C union B intersection C. Okay, this is with minus. With the help of this formula, I written this. Okay, next. Here, as continuation. Here it is. So I got finally probability of A union B union C equal to, I written this is one single set. Okay, it is equal to, we got probability of A. Yes, I'm writing same step here. Probability of A plus A intersection B plus probability of C minus, multiplied with minus symbol before that C. Again, it is again in the formula of P of A union B. P of A union B. Probability of union B. Assume this A intersection C is A, B intersection C is B. So again, it is a combination of, again, we are going to use same this addition theorem on probability on two events formula. Okay, apply this formula. Addition theorem on two events on probability, that is addition theorem on two events. A and B equal to P of A plus P of B minus P of intersection B. Again, we are going to apply same this result one more time. But in the place of A, here I have A intersection C. In the place of B, I have B intersection C. So expand this theorem. So minus of probability of A union B formula. Probability of A C plus probability of B intersection C minus probability of A intersection B. A means A intersection C intersection B intersection C. Okay. Is it clear? So probability, no, let us take with multiplication with minus symbol. So finally we will get P of A plus P of B. First I'll write this P of C first. P of C, next minus P of A intersection B. Okay, next minus P of B intersection C. First I'll going to write this P intersection C minus A intersection C minus P of A intersection C minus of minus plus P of A intersection C. Yes, A intersection C intersection B intersection C means it is C is repeated twice, so it is a intersection of triple quantity. A intersection C intersection B intersection C is there. So I'll write this is A intersection B intersection C. So A intersection B intersection C. So this is our theorem. Probability of A union B union C equal to, this is our result. So probability of A union B equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of B intersection C minus probability of A intersection C plus probability of triple intersection A intersection B intersection C. This is addition theorem on probability. Okay, so this is about addition theorem on probability on two events as well as on three events. Similarly, we can extend these formula up to n events also. In your final exam, maximum they will have the up to n events. Okay, I will write how to expand this theorem. If probability, addition theorem and probability on n events is given in our final exam. So first, let us do the proof of 2 events first. Then we can expand this is similarly to 3 events, 4 events up to n events. Yes, I will show it here. So this is similarly addition theorem on probability on n events. All n events are mutual exclusive events. Therefore, the result is here. So here, just first go through the what happened in a 2 events case, 3 events case, like that. Okay, if it is here, only 2 events are there. Probability of A and B equal to first their sum of their individuals, then subtraction. Their subtraction. Similarly, if it is 3 events, A and B is equal to first sum of their individuals, then subtraction of two individuals, then addition of 3 intersections. So alternately, it is plus minus. So this is first combination. This is 2 intersection. Next, third intersection. Similarly, probability of A1 union, A2 union, then up to union AN. Then these results will become first sum of their individuals. Probability of A1 plus probability of A2 plus up to probability of AN. Next, minus 2 intersections. So probability of A1 intersection A2 minus probability of A2 intersection A3 minus that is up to probability of AN minus 1 intersection AN. This is okay. Next, plus addition 3 intersections. Probability of A1 intersection A2 intersection A3. Next, plus probability of A2 intersection A3 intersection A4. Plus up to probability of AN minus 2 intersection, that is whatever last one, plus all combinations intersections, plus alternative will get the plus minus probability of A1 intersection, A2 intersection up to intersection AN. This is addition theorem on probability. Instead of writing this, you can write in this manner also. Yes, I will show it. That is probability of A1 union A2 union up to union AN equal to first sum of pi equal to 1 to n p of individual events A. Next, minus sum of I equal to 1 to n AI intersection AI plus of I equal to 1 to n AI intersection AI plus 1 intersection AI plus 2. This is minus that is then last sum of I equal to 1 to n AI intersection AI plus 1 intersection up to intersection AN. This is okay. I plus n. Sorry, this I plus. This is probability addition theorem on probability on n events. Okay. Yes. On this, let me do 1 or 2 examples. Here, suppose here, if you throw examples on addition theorem, if you throw 2 dice, question is what is the probability that the sum of 2 out faces is exactly let us take some 8 when 2 dice are thrown simultaneously. 2 dice are thrown simultaneously. Okay, so my question is whenever 2 dice are thrown, What is our question? Whenever two dice are thrown simultaneously and the sum of two out faces will be 8 into. Okay, it should be 8. So it means whenever two dice are thrown simultaneously, first we need to identify what is the minimum sum, what is the maximum sum. If you throw one single die, what about outcomes? What about results? Either 1 or 2 or 3 or 4 or up to 6. Similarly, if you throw another die, the result is either 1 or 2 or up to 6. But what is my question? The sum of these two out faces will be 8. So first, before going to start this problem, first we have to identify whenever two dice are thrown, what is minimum sum of two out faces? What is maximum sum of two out faces? So here, if it is first die is 1, shows 1, second die also shows 1. The sum will be 2, 1 plus 1. So that is the least sum. We cannot get either sum is 1 or 0 because first die is, if we show it is 1, second die also show 1. Therefore, 1 plus 1 it is 2. So the minimum sum is 2. And if you throw maximum, coming to the maximum sum. So on first die, if it is show 6 number, and a second die, it is show 6 number. So 6 plus 6, it is 12. So the maximum sum, when maximum sum of two out faces, whenever two dice are thrown, it is 6. And the minimum sum is 2. So the sum is lies in between 2 to 6, 12. 2 to 12. Minimum sum is 2, maximum sum is 12. So whenever two dice are thrown simultaneously, the sum of two out faces, will be from 2 to 12. But in this question is asking the sum of two out faces will be exactly 8. So 8 means first write down the combinations. See here, if it is first die is 1 and second die we cannot get the 7 because maximum is 6 number only. So first die is 2, then second die is 6, then sum will be 8. Like that we have to write all possible outcomes. Before that, whenever two dice are thrown, what is exhaustive event? 6 to the power of 2. That is 36 events we will get. The possible sum of the combinations will be 36 combinations we will get. 6 into 6. So out of 36, my question is, what is the sum is exactly 8. How many among 36 combinations? We have to write that combinations. I will show it here. See here, whenever two dice are thrown, exhaustive event is 6 square, that is 36. Among that, favorable chances. The sum is 8. Sum of probability of sum of two out faces must be equal to 8. So that combinations will be first write down all that combinations. If it is, this is die 1, this is die 2. Combinations will be, this is 2, then this will be 6. Okay. Next one more combination. This is 3, it will be 5. Next, it will be 4. Next, another one is 4. Okay. And interchange this. If it is first die is 6, second die show 2. If it is first die 5, second die is 3, then the sum is 8. And this is 4, 4. We can't write this 4, 4 because it is repeated case. First one is 4, second one 4. Again, it is, if you write 4, 4, this will be repeated. So write down only one time. So among 36 combinations, we have only 5 chances whose sum will be exactly 8. They are 2, 6, 3, 5, 4, 4, 6, 2, and 5. These are the favorable chances. How many chances are there? 5. Therefore, these are the favorable chances. These are the exhaustive events. Therefore, the probability of getting sum equal to 8 is equal to favorable outcome by exhaustive event. This is the formula. What is favorable? 5. What is exhaustive? 36. So this is also 35 by 36. Okay. Similarly, if I say the probability, another question. Similarly, probability of whose sum is 12. How many combinations will get? Sum is exactly 12. So there is a first die shows 6, second die shows 6. So this is the only one situation among 36 cases. Therefore, favorable outcome by exhaustive event means this is one chance by 36. Similarly, what is sum is 6. Yes, write down the combinations 1 5 2 4 3 3. Reverse 5 1 4 2. So I can here also 5 combinations 5 by 36. What is sum is 7? Like that you can prepare any questions, but whose sum is from 2 to 12. Okay, so sum is 7. 6 1 reverse case. 2 5 5 7 5 2. Next 3 4 4 3. Next. So these are the only 6 combinations out of 36. So 6 by 36 means 1 by 6 chances there. Okay. These are the different problems which are based on addition theorem on probability. Next. Let me discuss multiplication theorem on probability. A and B are any two events, and before that multiplication theorem probability, first we are going to discuss conditional events first. If you know the knowledge on conditional events, then multiplication. So I will explain the conditional events here first. See here. Conditional events. Conditional events first. Conditional events. Conditional events means two or more events are said to be conditional events to each other. Two or more events are said to be conditional events to each other if in only one single experiment, first one of the event can be selected from the same experiment only. The second event will be occurred in that same experiment. In that case, both two events A and B are called conditional events to each other. I'll show it here. So in an experiment, in any random experiment, suppose A is the first occurrent event. In any random experiment, let A be the first occurrent event. First occurrent event, and let B be the another event. It can be occurred. It can be second occurrent event. You can say second occurrent event. Event in same random experiment. In the same random experiment. Is it clear? So in one single experiment, I am taking two events, but based on certain condition. A is the first occurrent event. Then from this A itself, I'm going to take B be the second occurrent event. For example, here, simply I will explain this with one set notation. Let us suppose A equal to N equal to total exhaustive events. Let us suppose 1, 2, 3, 4, 5. Let us suppose I am going to take in any experiment, we have 5 events. First, from these 5 events, I'm going from which set I'm going to select A? Yes, A is we are taken from N. So A is subset of N. This is the first existing event or first occurrent event. From this A itself, I'm going to take another event B. I'm not selecting the B from N. I'm selecting the B from A. So it is 1, 2, let us suppose. So here B is occurred subset from A. Of course, B is subset to N also, but we are selecting B from A. So already A is existing from N. From the existing event itself, I am selecting the one more event B. So like this, if you select in this situation, A, B are called conditional events to each other. So afterwards, B will be occurred in the same experiment. Then if it is selection is like this, then we can say both A and B are conditional events to each other. So here, which is the first occurrent event? A is the first occurrent event. So write down A like this, and this is B. So we can denote the conditional events notation like this. B gives A. We can write this is B gives A. It means A is the first occurrent event. In that same random experiment, B will be occurred second. Okay. A is the first occurrent event. Then afterwards, B will be occurred in that same random experiment. So in this situation, B and A are called conditional events to each other. Okay, and these probability is denoted by these. If you apply the probability on such type of events, then that probability is called conditional probability. So if I say probability of B gives A means in these kind of events are known as conditional probability in between A and B. So here, which is first occurrent event? A is the first occurrent means probability of A does not equal to 0. Means if it is A is existing, from that only we are picking B. So if A is not A having, because whatever the first occurrent event, that probability must be not equal to 0. Then only we can pick up one more event B from A. Okay, that's why I am writing P of B gives A means here A is the first occurrent event, B is the second occurrent event in that same random experiment under the condition P of A not equal to B. Similarly, if I write like this, A gives B means which is the first? We can read this is A gives event, then afterwards A will be occurred in that same random experiment. Then A, B are called conditional events to each other. If I apply the probability on such type of events, then that probability is called conditional probability. It is denoted by P of A gives B. P of A gives B means B is the first occurrent event, then A is occurred in that same random experiment. And here, whatever the first occurrent event is there, that probability must be not equal to 0. First occurrent event. That's why I am putting probability of B does not equal to 0. So probability of A gives B means B is the first occurrent event, then A will be occurred in that same random experiment. In this here, these two are the conditional probabilities, or in these two events are called conditional events. If I apply the probability on such type of events, that is known as conditional probability. Okay. Next, by using this, I can define the multiplication theorem. Here, by using these conditional events, I can define the multiplication theorem on probability. Here, I'll show you multiplication theorem on probability. This is second theorem. Previously, I applied, I finished the addition theorem on probability. This is multiplication theorem. Multiplication theorem on probability statement. If based on this, you can expand the base theorem. First, listen this. Multiplication theorem on probability statement. If A and B are any two events, then probability of A intersection B equal to is probability of A intersection B equal to probability of A into probability of B gives A. This is multiplication theorem. If I write like this, which is the first occurrent event, A is the first occurrent event, then B will be occurred in that same random experiment. This is the second occurrent event. So whatever the first occurrent event is there, that probability must be not equal to 0. Similarly, you can write same statement in this another manner also. Probability of A intersection B equal to probability of B into probability of A gives B. So if I write like this, A gives B means B is the first occurrent. So A is the first occurrent event, B is the first occurrent event, and A is the second occurrent event. If I write like this, what about condition? whatever the first occurrent event is there, that probability must be not equal to 0. So this is conditional probability theorem or multiplication theorem on probability. In this here, how many events I have taken? Only 2 events. If we expand this theorem up to n events, that is known as Bayes theorem. Okay, I will explain the proof of that Bayes theorem. So what I'm saying, conditional probability theorem or multiplication theorem on probability, it will use only on 2 events. If I take 2 events, among the 2 events, I am writing the P of A intersection be equal to P of A into P of B gives A. Whenever P of A not equal to 0 into P of A gives B, means here B is the first occurrent event. So probability of B does not equal to 0. This is multiplication theorem on probability or condition theorem on probability. In this, I have taken only 2 events. Okay, and if we expand this theorem to up to n events, yes, up to n events, that is known as Bayes theorem on probability. That is the most important topic for your final exam purpose. I will explain the statement as well as proof. Okay, just listen. Yes, see. So in this multiplication theorem probability, now expand this same theorem. Bayes theorem. This is one of the most important topic. Bayes, it is scientist name. Bayes theorem. So this is extension theorem on multiplication theorem. Okay, Bayes theorem. What about statement? Come to the statement. Let A1, A2 lead up to AN. As I am expanding up to n events. Yes, in the question paper in your final exam, they don't give the statement. This is the named theorem. You have to write a statement by your own as well as proof also. So just they will be the question, state and your own. Okay. So first listen statement. Are n mutually exclusive events, means they are disjoint events. Okay. Simply they are disjoint events, and B be the any, as I am taking one arbitrary event. B be the any arbitrary event which is subset to all AI's. It means B is subset of A1, comma, B is subset of A2, comma, up to B is subset to AN. So I am taking an arbitrary event B, which is subset to A1 as well as A2 as well as A3 up to AN. And whatever the event we are going to take B, that probability must be not equal to 0. And this is also includes in the statement itself. And probability of B not equal to 0. Then the Bayes theorem statement in mutual exclusive events, and B is any arbitrary event which is subset to all A's, and probability of B not equal to 0. Then we have to prove that probability of A gives B equal to, yes, which is first occurrent event here? Is it A or B? A gives me means B is the first occurrent event. That's why in the statement itself, I have taken probability of B not equal to 0. Okay. So probability of A gives B equal to probability of A into probability of B gives A divided by sum of I equal to 1 to n. Same this result right here. Probability of A into probability of B gives A. This is Bayes theorem, most important topic. So what we have to prove, probability of A gives B equal to probability of A into probability of B gives A divided by same this is in numerator it is ith event, it shows ith probability. In denominator it will shows complete expected mathematical expectation value. We can call this as a mathematical expectation. This is complete sum of all events, event with corresponding probability, event with corresponding occurring probability. So I equal to n, P of A into P of B gives AI. Now coming to the proof of this Bayes theorem proof. Here, proof of Bayes theorem. So first, before going to start this proof, just I will explain this entire proof in one single Venn diagram. See here. Listen this way. Just understand this figure. Then everything you must write by your own words. Okay. How many? This is Venn diagram taking. How many events we are taken? In mutual exclusive events. Let us suppose this is A1. This is A2. This is A3. A4, A5, A6, A7, and up to AN. This is, let's suppose, AN. And all are touching, but there is no any common region. I'm not taking A1 into A2, A3, A4, and up to this is AN. Okay, in mutually exclusive events. Right? Is it clear? AN minus 1 divided up to. So all these are mutual exclusions. Is it clear? Yes. They are touching, but there is no common region. I'm not taking the common region here. I'm not taking common region here. Just they are touching like this. Circles, two circles touching like this. Okay, or like this you can take. There is no any common region between these events. And what is the nature of B? A1 and B, A2 and B, like that A and B. So let us take B is the common region. It is touching each and every individual. So assume this is B. I am taking this is B. Is it clear? This is B event. Is it B subset of A1? Yes. This is common portion is existing. Is it B subset of A2? Yes. This is common portion is existing. Similarly, B subset of A3 and B subset of A4, like that B subset of AN also. So it is subset to each and every individual events. Now the figure is like this, then we have to prove this result. P of A gives B equal to this. Now for proving this result, now I am going to use mathematical multiplication theorem on probability, this statement. So we know that, come to the proof, we know that the multiplication theorem on probability is, what about the theorem? P of A intersection B. P of A intersection B equal to P of A into P of B gives A, or it is same as P of A intersection B equal to, or P of B into P of A gives B, and this is exist whenever first occurrence P of A not equal to 0, and this is exist P of B not equal to multiplication theorem from same statement I written here. This statement I am using multiplication theorem. Now assume this is equation number 1, this is equation number 2. But in this here, I have taken only 2 events, A and B. But in our statement, how many events we have? N events. So just wherever A is there, just replace AI for all I equal to 1 to A. Just in the place of A, I am putting AI. And here also AI. Okay. Is A. For all I equal to where? 1, 2, 3, 4 up to N. So see here, equation 1, what about equation 1? P of A intersection B equal this, and equation 2 also P of A intersection B equal this. So here equation 1 and 2 are same, because this is A intersection B, this is also A intersection B. So if two left side quantities are equal, then this right side value is also equal. So here equation 1 equal to equation 2, or equation 1 and 2 are same. Therefore, equating this, P of AI into P of B gives A, which is equal to this, P of B into P of A gives B. Okay, these two are same. Now, what is our result? See the Bayes theorem statement. What is our Bayes theorem statement? Where it is? In minute. Yes. Bayes theorem shows that. What is Bayes theorem? So I want to prove P of A gives B equal to P of A into P of B gives A divided by this. So from these two, shall I write P of A gives B? I want to. So here it is there. P of A gives B equal to P of AI into P of B gives A. Bring this B to left side. This P of, I'll write once again this, A gives B equal to P of AI into P of B gives A divided by P of B. Yes. Assume this is equation number 3. Here, almost 50% of the theorem I got here. P of A gives B equal to P of A gives B equal to P of A into P of B gives A. P of A into P of B gives A. Divided by, instead of this, I got this is P of B. So, in the denominator, I want to prove a summation I equal to 1 to n P of A into P of B gives A. So, but here we got P of B. So, it is enough to show that for finishing this theorem, it is enough to show that P of B equal to this result. If I prove P of B equal to this, then our entire theorem will be over. So, for proving that one, I can see it. So, what is this? So, it is enough to show that it is enough to show that P of B equal to what we have to prove? P of B equal to this entire result. Yes, denominator part. Summation I equal to 1 to n P of AI. So this is we have to prove. For proving this result, again, come to a statement. In the statement, what is the nature of B? Is when B is the subset of all A's. So B is subset of A1, B is subset of A2, similarly B is subset of AN. So according to this here, A1, A2, AN are mutually exclusive events, and B is any arbitrary event which is subject to all A's. Means I am using this statement here. So here B is subset to A1, B is subset to A2, that is up to B is subset to AN. Okay, and from the set theory, if here A is B sub A is big set, B is small set. If B is subset to A, then what about B intersection A and what about B union A? B intersection A will become the smallest set B. Why? Because B is subset A and B is subset to B itself. So every set is subset itself with B is the common subset to both A and B. That's why B intersection A will become B. And what is B union A? B union A means we will get big set A. But here I don't want to this. I'm going to use this result. If B subset of A means B intersection A equal to B, the smallest set or the combined common set. So I am using this result here. Is it indicates what is B intersection A1? Yes, which is smallest set? B is smallest set, A is big set means we'll get the intersection is smallest set. So B intersection A will become B. Similarly, B is subset to A2. This result. Again, B intersection A2 will become, again it is B. Like that, if you take up to nth event, B subset of AN, it implies B intersection AN is also equal to B. So add all this. So B intersection A1 is B, B intersection A2 equal to B, up to B intersection AN also B. Therefore, I am writing here B equal to B union, B union, B union up to union B n times. For getting Bayes theorem, just I am using the result this one. So write B as a B union, B union. What is B union, B union? Again, it is B equal to B. So B equal to will get B only. But in B, let's say I'm writing B union, B union, B union, B. So B equal to this B intersection A1. Next, B union. Again, for second B, I'm writing this second quantity. Union B intersection A2. Like that. Union third B like that. Up to nth B, I'm going to write B intersection AN. So just I'm writing In the place of B intersection A1. Again, B intersection A1 is B only. B intersection A2 is B only. Like this, okay? Now take probability on both sides. Take probability or apply probability on both sides. Then we'll get probability of B equal to probability of B intersection A1 union B intersection A2 union B intersection AN. But in the statement itself is giving what is the nature of A1, A2, A3 up to AN? They are mutually exclusive events. Yes, here also given here. A1, A2, AN are mutually exclusive events. Means A1, A2, A3 up to AN are disjoint sets. There is no any common region between A1, A2, A2, A3 like that AN, A1. Okay. So all mutual exclusive events means according to addition theorem on probability, axioms of probability, the fundamentals of axioms of probability. Any two events are disjoint, then their union will become sum of their individuals. So here B1, B intersection A1 disjoint from B intersection A2. It is disjoint from up to B intersection AN. Therefore, all these are mutually exclusive events. Then their union will become sum of their individuals. Therefore, probability of B intersection A1 plus probability of B intersection A2 plus that is up to probability of B intersection AN. Why I am writing this? Since the condition is A1, A2 that is up to AN are mutually exclusive or simply disjoint sets, disjoint events. That's why I'm writing their union will become sum of their individuals. So let's write this is probability of B intersection A1, B intersection A2, or simply shall I write this is equal to summation I equal to 1 to N B intersection AI. If you put I equal to 1, we'll get this plus I equal to this like that. Okay. So we know that A intersection B is always equal to B intersection A. I'll write this is summation I equal to N P of AI intersection B. Okay. This is I got P of B value. Next, here again I'll going to use this first result. What about that? From multiplication theorem, I got two equations. P of A intersection B equal to P of A into P of B gives AI. Similarly, P of A intersection B equal to P of B into P of A gives B. So I'm using this first equation. So in the place of P of A intersection B equal to, I'll write this combination, this quantity. Here I have P of A intersection B equal to. So this is equal to summation I equal to 1 to N P of AI into P of B gives AI. Since from equation 1, here P of AI probability must be not equal to 0. Since from equation 1, this is P of B value. Okay. So finally, I proved P of B equal this. So in the beginning itself, I written it is enough to show that this denominator part, it is enough to show that P of B equal to summation I equal to 10, P of A into P of B gives A. Yes, I proved. So P of B equal to summation I equal to 10, P of B A into P of B gives A. So now this is assume this is equation number 4. Substitute equation 4 in equation 3. It shows base theorem result. So finally, we'll get LIDF. Finally, we'll get from equation 3 and 4. So what is equation 3? Yes, we have equation 3 is, I'll write here. 1 minute. So from equation 3 and 4, or substitute equation 4 in equation 3. What is equation 3? Equation 3 implies probability of A gives B is equal to probability of AI into probability of B gives AI divided by probability of B. But what is probability of B value? We got this is probability of B. So substitute. Sorry. Substitute that probability value here. So substitute the probability value. So probability of AI into probability of B gives AI divided by probability of B value. This is sum of I equal to 1 to n, sum of probability of I equal to 1 to n, P of A into P of B gives AI. This is probability of A gives B formula. This is called Bayes theorem results here. This is of take where it is statement. Yes, this is probability of A gives B equal to this one. Okay, you put same the result here. Probability of A gives B equal to probability of A into probability of B gives A divided by summation I equal to 1 to n P of A into probability of P of A into P of B gives A. This is Bayes theorem statement and proof in probability. Okay. So this is about the Bayes theorem result. So among these three theorems, definitely we'll get the one theorem on your final exam. Either it may be addition theorem or multiplication theorem. Multiplication theorem extension topic is nothing but Bayes theorem. Okay. So please do practice problems on this Bayes theorem. Okay. So almost it is the time 2:34. Okay, we finished probability definition, probability axioms, general examples, as well as addition theorem on probability on 2 events, on 3 events, on up to n events. Similarly, multiplication theorem. Finally, we finished this Bayes theorem, that is extension part of multiplication theorem. If you take only 2 events, that shows multiplication theorem. If you take up to n events, that multiplication theorem can be extended to Bayes theorem. Okay, so Bayes theorem statement is one of the most important in this. A1, A2, AN are n mutually exclusive events, and B is the subset of all AIs. That is B subset of A1, B subset of A2 up to B subset of AN, and probability of B, that arbitrary event probability must be not equal to 0. Then probability of Bayes theorem states that, Bayes theorem states that probability of A gives B equal to probability of A into probability of B gives A divided by same that numerator with summation n events. Summation I equal to 1 to n P of A into P of probability of B gives AI. This is Bayes theorem statement and proof. Okay, just we have to practice 1 or 2 problems on Bayes theorem. And this is the complete last 4 units. Okay. Okay, stop the class because the time is already, it is 2:36. Okay, and dear students, I wish you all the best to all of you for your final exam purpose. Okay, yes, we'll stop.